Okay, what we want to do next, now that we remember our definitions, is we want to go through each of these 12 functions and see if we can answer a handful of questions about them. So we're going to start with parent graph number 1, which is the linear function. The linear function is probably the first function you ever learned about in math. Just y equals x is that parent function for the linear graph. And so what are some points on this graph? Well, it's a graph that starts at the origin and has a slope of 1. It's a linear function, and so we're going to have something that looks like this. I'm going to do this dashed because I'm not going to be able to draw a real good straight line through that. And so there's our linear function. Okay, what would you say the domain of this function is? Well, that's the x values read from left to right. And since there aren't any restrictions on our linear graph, we're going to have negative infinity to infinity be our domain. We're also going to have the range be negative infinity to infinity, since those are the y values read from bottom to top. Now, is there any symmetry in the graph? Hopefully you said that there is some symmetry in the origin, okay, which essentially means this, that if you took this portion of the graph in the first quadrant and you reflected it over the x-axis, and then you reflected that over the y-axis, that the graph would be sitting on top of itself. And so remember, again, symmetry to the origin means that this function is odd. Boundedness. Is this graph either bounded above or bounded below? Well, no, because the range, if you take a look at the range, it is unbounded. And so therefore, this linear function is not bounded. Okay, are there any asymptotes? No, not applicable. Discontinuities? No, this graph is able to be drawn without picking up your pencil, so that's going to be not applicable. Where is this graph increasing or decreasing? Well, reading from left to right, the graph is always going up, and so this graph will always be increasing on the entire domain, negative infinity to infinity. Extrema, remember, means maxes or mins. So are there any turns in this graph? Does it have any maximum or minimum points? The answer to that would be no, it doesn't. And then finally, the end behavior, we want to write two limit statements. So the limit as x goes to infinity, and we'll just call the function f of x. Well, as x goes to infinity, what's happening to the y values? They are increasing without bound, and so that will be positive infinity. And then the other end behavior limit, the left end of the function, as x goes to negative infinity, is going to be negative infinity, because if you look this direction at the left side of the graph, the y values are decreasing without bound. So that limit is going to equal to negative infinity. Okay, our second parent function is the quadratic function, so that would be y is equal to x to the second power. And if we want to graph this function, let's just plug in a couple of points. So I know that if I plug in 0 for x, 0 squared is 0. And if I plug in 1, that's going to give me 1 squared, which is 1. And if I plug in 2, 2 squared is 4. And so that's going to be this part right here. And then I know that the quadratic has another side to it as well. And so I can come over here and plot the other side of my quadratic. Okay, what would we say the domain is here? Well, there are no restrictions on x squared, and so that's going to be negative infinity to infinity. The range are the y values read from bottom to top, so the smallest y coordinate on that graph is 0. It's going to be included, since we actually have a point that's touching 0 on the y-axis, and then it goes up to infinity. Symmetry. Well, this graph is symmetric to the y-axis, as you can clearly see from the picture, which means that the function is even. Boundedness. This graph is bounded below, and you can see that for a couple of reasons. Notice that I can draw a horizontal line below the graph, and you can see that the range on the bottom side, on the left side there, is not infinity or negative infinity. So that means that this is going to be bounded below. Okay, does it have any asymptotes? No, it does not. Does it have any discontinuities? No, it does not. We can graph it without picking up our pencil. Is it increasing or decreasing? Well, it actually changes, doesn't it? So it actually starts off as a decreasing function, and that's from negative infinity until 0, and then it starts to increase starting at 0 and going to infinity. Does it have any extrema? Well, yes it does. Take a look here. This point right here on the parent function is a minimum, and you could be even more specific and say that it's an absolute minimum if you wanted to, and it's a local minimum, but I'll just say minimum at 0, 0. Okay, and then finally, end behavior. We want to write two limit statements in this case. And so first, limit as x goes to infinity of this function, f of x. As x goes to infinity, that's the right side of the graph. You can see that the y values are increasing without bound, which will make that limit infinity. And then the limit as x goes to negative infinity of f of x would be the left end behavior, and you'll see that on the left side the y values are also going to infinity. Okay, for the cubic function we have the equation y is equal to x cubed, and so if we want to graph this we could plug in a couple of points. 0 cubed is 0, 1 cubed is 1, and 2 cubed is 8, which is actually going to take me off the graph way up here. And then you could also do the negative of those. Negative 1 cubed gives you negative 1, and negative 2 cubed gives you negative 8, and so we would have these points as well, and so this would look something like this. Okay, so what will the domain be? Well, there are no restrictions. It touches every x value on the graph, and so negative infinity to infinity. The range also touches every y value, and so that will also be negative infinity to infinity. There is some symmetry to this graph. It has symmetry to the origin, which means that it is going to be odd. It is not bounded, since the range is negative infinity to infinity. So really you could either say not applicable or not bounded there. It does not have any asymptotes, nor does it have any discontinuities. This function is always increasing on its entire domain from negative infinity to infinity. It does not have any maximums or minimums, and the end behavior is very similar to the end behavior of the linear function y equals x. So we'll say the limit as x goes to infinity of f of x. Well, the right side of the graph, the y values are increasing without bound, and so that limit is going to equal to infinity. And let's see if I have enough room to fit this in here. Limit as x goes to negative infinity of f of x. This limit is going to equal to negative infinity, since on the left side of the graph the y values decrease without bound. Okay, for parent function 4, we have what's called the reciprocal function, which is going to be y is equal to 1 over x. So notice that denominator there. If we try to plug in a couple of points, I can't plug in 0 because 1 over 0 is undefined. But if I plug in 1, 1 over 1 is 1. And if I plug in negative 1, then 1 over negative 1 is negative 1. And what we end up having here is a horizontal asymptote. So hopefully you can see that on the picture. A horizontal asymptote at y is equal to 0, and a vertical asymptote at x is equal to 0. And then we have two pieces of our graph, one that comes down and through that point like that, and another piece that comes through that point and down that direction. So that's what our reciprocal function looks like. So what is the domain of this? What x values is this graph touching? Everything except for 0. So that's going to be negative infinity to 0, not including 0, and then 0 to infinity. What's the range of the graph? Well, those are the y values read from bottom to top. So this graph on the y-axis touches every single y-coordinate except for 0. So that means we're going to have the exact same range as we did domain, negative infinity to 0 and 0 to infinity. Now, does this have any symmetry? You bet it does. It has symmetry to the origin, which again means it is odd. Is it bounded, either above or below? Well, if you look at the range, you can clearly see that this graph does not have any boundedness. It does have two asymptotes. It has a vertical asymptote at x equals 0, and it has a horizontal asymptote at y equals 0. It does have a point of discontinuity. X equals 0 is what we called last time an infinite discontinuity because of the vertical asymptote that is occurring there. So that's an infinite discontinuity. Now, is the graph increasing or decreasing or both? Well, let's take a look here, reading from left to right. This graph is getting smaller as you go along and keeps going down. Then when you pick up here, again, be careful with the arrows. You don't want to be misled. You're reading from left to right. This graph is going down as you read from left to right, and so this function is always decreasing, and it's doing so on its entire domain. Okay, extrema. No, there are not any extrema. There are no maximums or minimums to that graph. And then finally, end behavior. Let's take a look at that. The limit as x approaches infinity, that would be the right side of this graph. And so as we approach infinity on the right side, notice that the graph is approaching this horizontal asymptote of y equals 0, which means that that limit is going to equal to 0. And then the other end behavior limit as x goes to negative infinity of f of x, and I'm running out of space, so I'm going to have to do it down here. Notice that that will also be 0 because negative infinity is the left side of the graph, and the graph is approaching the y value 0 as we go towards negative infinity on the x-axis. Okay, for your square root function, you've got the equation y is equal to the square root of x. And so if we were going to graph this, we would just choose a couple of points. The square root of 0 is 0. The square root of 1 is 1. And the square root of 4 is going to be 2. And so we've got something that looks something similar to that. And so we can take a look and see what the domain is. The domain is going to start on the x-axis at 0 and go all the way to infinity, and the range is going to do the same thing. It's going to go from 0 to infinity. Now, is there any symmetry to this graph? This is actually the first of our 12 functions that doesn't have any symmetry to it. Is there any boundedness? Yes, there is boundedness. It is bounded below. Take a look at that range. The bottom portion of that range is not negative infinity, and so therefore it is bounded below. Another way to think about it is you can draw a horizontal line that will go underneath the function and never touch it. Are there any asymptotes? No, there are not. Are there any points of discontinuity? No, there are not. This function is always increasing on its entire domain. There are no local mins or maxes on the square root function. Remember, in order for something to be a local min or max, there's got to be a right side and a left side to the point. There is no left side to the point 0, 0, but it is the smallest point on the entire graph. And so what we would say is that it has an absolute minimum, and that absolute minimum occurs at, 0, 0. Okay, and then finally, end behavior. The end behavior is going to be a little different here because the range is not negative infinity to infinity. And so let's look first at the limit as x approaches the right end of the graph, which would be f of x. In that case, well, if we take a look here, as x approaches infinity, the y values are getting larger. And so that limit is going to equal to infinity. But for the other side, we're not going to put the limit as x approaches negative infinity because this graph never approaches negative infinity. The furthest left it ever approaches is 0, and it does that from the positive side of 0. That's why I put the little superscript plus sign there to indicate from the right side of 0 or from the positive side of 0 of the function f of x. And what y value is the graph approaching? As we approach x equals to 0 from the right, the y value that it's approaching is 0. All right, for the exponential function, we have the equation y is equal e to the x. And e is not the only base that we care about, but in calculus it is definitely the most common one, so we're going to use e to the x here. And so if I just try a couple of points, let's try 0. That's going to give me the y value e to the 0, which means that that's equal to 1, since anything raised to the 0 power is 1. And so what this graph looks like is it actually comes right off of the x-axis like this, goes through that point, and then increases very quickly from there. And that's why it's called exponential. You might have heard of exponential growth before, and that's what it is right there. So domain, there are no restrictions here, so that's going to be negative infinity to infinity. The range is going to be from 0 to infinity, but we are never actually touching y equals 0 because that is a horizontal asymptote. And so this is going to be not including the value of 0 in the range. This graph does not have any symmetry. It does have boundedness. It is bounded. Hopefully you are picking up on that. Bounded below. It does have an asymptote, more specifically a horizontal asymptote at y is equal to 0. There are no points of discontinuity on the exponential function. It is always an increasing function on its entire domain, so from negative infinity to infinity. There are no local extrema on the exponential function, and the end behavior limits are as follows. The limit as x goes to infinity of f of x is going to equal to infinity, since as you approach infinity on the x-axis, the y values are increasing without bound. And then the other end behavior limit is the limit as x goes to negative infinity of f of x, and you can see clearly that as you follow along towards negative infinity on the x-axis, the y-coordinate that graph is approaching is equal to 0.